over to you.
Thank you, George. Thank you, LifeArc. Well done for being the discerning few that have stayed, only because actually this is a white space opportunity. This is something which is entirely untapped, entirely new. And as a result, hopefully we'll be able to show you some things that are interesting. So yes, as George said, I work between two places. 80% of my time I run a group at the Crick, which is one of the most exciting places to do science in the world at the moment. And 20% of the time I run a national service at Great Ormond Street for these very rare skin disorders, which we can't currently treat. And for those of you that thought pediatric dermatology is just a bit of eczema, these are pictures of my patients. These are examples of the things they have to go to school with every day. You can remember having a spot on your nose when you were 15, I'm sure, and how you didn't want to go out of the house. Well, you can probably imagine what these things do to people day in, day out. And not only are they very difficult to live with, but every time they come and see me, we say, we've got nothing to give you, literally nothing to give you. So that's the background to why we do what we do. And what we set out to do, I think if Tom Cruise can do this, maybe we can do that, is actually to take a broad platform type approach to these diseases. And the reason we can do that is because they are linked by a common mechanism. So although each disease is caused by a different gene, they are linked by having the same mechanism. So what do I mean by that? These are some of the genes that my lab has found in the last decade. When we started doing this, we didn't know what caused any of them. And we figured that actually working out what caused them would probably be the best place to start for therapeutics. And what we found, fascinatingly, was that they are monogenic disorders. They have recurrent mutations, so very good for targeting in terms of therapies. And they occur during pregnancy. So all of us know we're very comfortable with Mendelian genetics because it's been around for so long. But mosaic disorders are the future. We are doing skin because we can see it. But they're now finding mosaic disorders in the brain, causing autism, mosaic disorders everywhere else we are pretty sure must exist. And when we set up a large tissue bank, we've now collected 2,000 patients and lots of samples here. What we found, in fact, was that these are oncogenic variants. So this we weren't expecting. But of course, in retrospect, makes perfect sense. So the same genes that are responsible for differentiation and proliferation during development are exactly the same genes that are responsible for differentiation and proliferation in cancer. So this is a rare disease opportunity which also has legs into cancer. In fact, it also has legs into common skin diseases, because as we get older, and I would absolutely put myself in that same category, we all keep getting new little spots and dots, and we have to go to the doctor. And if you've got aging parents like me, it's no fun, actually, getting things taken off and stitched up and surgically removed. Why don't we instead extrapolate these treatments for these rare disorders into the rare skin diseases, into the common skin diseases? And why can we do that? We can do that because the mutations are identical. Not just the same genes, the mutations are identical. So, one other key factor you need to know is that although patients come to me with skin disease, depending on when the mutation has hit during pregnancy, they may also have, in fact, usually do have other organs which are involved as well. I'm not going to talk about the neurocutaneous and the eye aspects of these diseases today, but again, there are other parts of this to treat. So when we first started finding the genes, it was quite exciting because I thought, oh, great, we'll just use all the oncology drugs that are there, and that's going to be fantastic. We're going to get quickly onto cures. And we have done a lot of work in repurposing, so compassionate trials, of many of them now, in silico drug screens and in vitro FDA-approved drug screens. And occasionally we strike it lucky and we get pretty good response. This one's a nice new one for cholesterol, so we can sometimes make these go away. The best we've got with the truly oncological type genes is this, so we can improve things a bit, we can settle down the disease a bit, but do not kid yourself that we're making this go away. We're not. We're just improving this. We're improving the itch and the inflammation, et cetera, et cetera. This is the best a MEK inhibitor can do for a patient with a BRAF fusion or an NRAS mutation. It's we think of NRAS and BRAF, we think we understand them because of cancer, but we don't actually. It turns out that although they are driving this disease, you give those types of inhibitors and they don't actually kill the cells. We would like to kill the cells. We would like to get rid of these. And why are they not working very well? They're not working very well for a very obvious reason, which is that when you use a small molecule, you target one in many pathways, and actually we want to target them all. We could spend our lives understanding these better. If I had the time and the money, I would love to, but I want to cure the diseases. So instead, we're going to target the genes, because targeting the genes, even if we don't understand all the pathways that we're affecting, should cure the disease if we're right. Don't forget, these are monogenic diseases. They don't have lots of additional mutations to worry about. So we moved on about 10 years ago to genetic therapies, but I've only been publishing recently on this because it's taken a while. We now have this pipeline where we go from the untreatable disease with our large tissue bank, and we have commercial approval to use the data in that tissue bank, through gene discovery to the targeted therapies, and we hope to a cure. And the reason we're doing them in parallel is because we have the patient groups for all the different diseases embedded in this, and we have, quite rightly, pressure from them all. So we're trying to scale this as a sort of an actual pipeline. I'm going to talk to you about two of these diseases today. So these two at the top. One is called congenital melanocytic Nevi syndrome. Dermatologists are not very original. This is a description. It just means brown birthmark. But it's a particular type of brown birthmark. We call it CMN for short. And the next one is more well known. We don't really know why, but it's called Sturge-Weber syndrome, and it's sort of got into the textbooks, so some of you may have heard of it. As you will all know, I'm preaching to the converted here, siRNA therapeutics are a major emerging area. And I'm sure, again, you all know, but just to reiterate the basic science, what we do with RNAi is we design a very simple molecule on the back of an envelope, which takes a second, and you test it out. And it is not something that requires a huge amount of drug development. And what it does is it goes in, it binds to the area of RNA that you don't like. In our case, we bind it exactly to the mutation that we don't like. And then it's degraded. So on a simple level, what you're doing is getting rid of the RNA that you don't want. Instead of having to wait for the protein, design something complicated to get rid of that. So the advantages, as I've sort of slightly alluded to already, rapid drug development, but also high specificity. The gene targets we're going for, NRAS, oncogenic mutations, these have been undruggable forever. There's beginnings of people designing things, but we've tested these against even the BRAF inhibitors that are around. We can get much higher specificity by knocking down the RNA at source than we can with protein level. And minimal off targets. And how do we know this? There's 7 siRNAs already FDA approved. They're in the market. Their side effect profile has been fantastic. Now, delivery has been the big thing with RNA. This is massively changing. Anybody that's sitting there thinking, they'll never deliver it, come and have a look at our data. Skin, for a start, super easy. So let's not forget, good place to start, but it's not only skin. And what we do with our RNAs is we take it to an extra level of specificity. We just target the mutant allele. So traditionally, genetic therapies that you're all aware of, or more commonly aware of, you'll be trying to replace something. You'll have multiple different genetic changes. Every person has a different one. You're trying to replace something that's a loss of function. Here, we have recurrent mutations. So they're the same in almost all the patients. And you have a normal copy of your allele of your gene that you want to preserve. So all we need to do is target the one that's mutated enough to get it down, and then all the protein you're making is from your normal allele. So what we're doing is dialing things down a little bit. Now, we've been looking at skin delivery, which I will not talk to you about today just because we don't have quite time, but we can also deliver this in other ways. So this is the first one. This is congenital melanocytic nevus, CMN syndrome. Amazing woman, now a doctor. And this disease, we found the genes for some years ago, but we were starting with targeting this NRAS missense down there because it's 70% of this disease. And we published this last year showing we could slow up the proliferation of the cells. Nice, we know we can do that anyway with a MEK inhibitor, so we were not particularly impressed. But what we were then able to show is that a single dose at time 0, here shown in 3 different patients, we go across our patient group to de-risk for when we get into clinical trials. And what we show here, the blue line, is caspase 3-7 activity. This is apoptosis, cell death. Single dose at time 0, all the cells die in the next week. And we've now done this in about 20 samples. What we've also shown is that knocking down just that mutated allele, you get 10-fold fewer off-targets than if you just knock down NRAS in general. Not really a surprise. And we went into a mouse model. We've shown knockdown. We've got more to show you, which is going to come out later this year, but I won't talk about it today. We've now designed this clinical trial, and we're very, very pleased to now have pharma investment. We've jumped over the VC stage and gone straight to pharma, and this is going to hopefully come to fruition quite soon. So our projection for these diseases is that they will come to my clinic, and instead of me saying, I'm sorry, there's nothing we can do, we will say, we'll make your diagnosis, we're going to start you on this therapy, and this should be curative. So this is siRNA therapy that may be the first cure. And the reason it may be the first cure is we know that in this single case worldwide, because I see a lot of these cases worldwide, this is the only one I've ever seen. But she's a patient of mine. We watched her for 18 years. She had the classic mutation, and it went away on its own. These cells are not needed. This is not a congenital malformation. This is an annoying disease that we should be able to get rid of. So that's where we're going with that one. Today, if you're looking for an investment opportunity or even just for interest, this is what we're looking for in terms of support. So this is Sturge-Weber syndrome. You can probably see there's a bit of redness on the side of this girl's face, and you can also probably see that she's blind in this eye. This is glaucoma from the same vascular problem that's on the skin, also affecting the eye, and it can also affect their brain. You can see here. And we found genes for these before too. You see pictures like this on the internet. Don't be fooled. Even the skin disease is horrible. This is what happens over time. And actually, this is the poshest clinic I could find, New York City clinic, where they're saying they've made this better like this. You can laser these to death. You can keep going. You will make some degree of difference, but even for the skin, this is poor. You can see you can have them all over. And over time, they produce more and more lumps and bumps. So, oh, that's another picture of the eyes. What we really wanted to do, though, as well, is to stop the neurological deterioration that these patients get. So we're going to use the skin as our first proof of concept and get safety data. So we're going to be putting our siRNA on the skin when we get some investment and take this one forward to clinical trial. So do it in patients that don't have the brain disease, show that it's safe, show that it reverses the birthmark on the face. But ultimately, we'd like to get at this neurological deterioration. And the reason is they're born normal. And by the end of the first year, they're seizing, they've got delay, and they're having stroke-like episodes. And then it becomes worse and worse. I know I've only got 1 minute left, so I'm going to whiz you through what we found. We looked at a well-known clinical sign, which was that there is actually calcium deposition in blood vessels in the head in this case. People used to think this was a non-specific finding. We went on to demonstrate that actually the problem is calcium signaling, and that what happens is that you get calcium at baseline and with stimulation, which is continuously released inside the cell and dragged in from the blood to keep this constant process going. So the patients are becoming profoundly hypocalcemic in the areas of their brain where the blood vessels are not right. We showed that the calcium level is connected to their chances of seizures, and we showed on histology that they have calcification of microvasculature. We can stop this by giving the siRNA either intrathecally or intravascularly with a decent LNP. So we should be able to stop the biology, prevent the continuation with our siRNA. So again, we have a plan for how to prevent this going forwards. So just to thank the real stars, which are my team, our funding, which includes some from the wonderful LifeArc, and to you for your attention. Thank you.
Thank you. Thank you, Veronica. I think there's some real signs of hope there, I think, for those patients who really don't have many options. We have a few minutes for questions. Not many, but a few minutes. Please, can you keep them really brief? There's a few on the right side of the room here. Oh, Matt.
Thank you. Matthew Wood from Oxford Harrington. Very impressive. Lots of questions, but just two very specific ones. I mean, have you had to develop a specific formulation for the siRNA on the skin? And how frequently do you need to dose your patients, at least in the first study you presented?
Two very good questions. We started using receptor-targeted LNPs because we thought we'd need it. We've now taken off the receptor targeting, and now we've taken off the LNP. Actually, for skin, it's not difficult. Everything we've tried gets it in. We can knock it down for a week with a single dose without doing anything fancy, but with backbone modifications, which we've done more recently, we can do for a bit longer. We actually don't want to knock it down for very long. We'd like to just have it in and out so you don't get it sticking around the circulation. And in terms of plan going forward for the clinical trial, we've got weekly doses for 6 weeks, and we think it should be gone.
Okay, there's some questions. There's someone with a microphone here. Go ahead.
John Isaac, Slingshot Therapeutics. It's super interesting. I really like the concept that mosaic genetic diseases are the way forwards. Super interesting. Do you use any specific chemistry for RNAi? Is it proprietary chemistry? Is it just...
Not proprietary chemistry. We use the Alnylam published backbone modifications, which are nice. Yeah.
And so for CNS disorders, would you be putting this into CSF? And how frequently would you need to dose, do you think?
So intrathecally, we think is a very good option. It depends if you've got a cure or if you've got something you need to treat over time. I think if you've got something that's a cure, intrathecal would be very acceptable, and you could give it regularly. We don't know how long you'd get knocked down that way for. If it was something you needed to give over time, you would need to use an intravascular approach with a proper LNP or something similar.
Thanks.
Thank you. We have time for one really quick question and a really short answer if anyone has a burning question. No?
Lovely.
That's also fine. You can also find Veronica at the break. Thank you very much.